or maybe let me start, or let me in the meantime make you the host,
Mhm.
make host. Oh, probably because if I log in first, then I'm the host.
Right.
Yes, now it is. Yeah, it is streamed on YouTube right now, I think.
Yes. Yep.
Yeah, got the notification. Yeah, I think we are.
Okay, probably we can start. Quite a lot of people joined today. Okay, let's start. So, are we recorded or is it automatically recorded?
It is recorded on YouTube automatically. So
Okay, great. So today it's our great pleasure to have Dr. Guo-Yi Zhu from University of Cologne. And he got his PhD from Tsinghua Universities and was a postdoc research associate at Max Planck Institute of Complex System at Dresden before he moved to University of Cologne. So Guo-Yi is an expert on tensor network and DMRG simulations for quantum many-body systems, and recently he had lots of interesting results on measurement-induced phase transitions, some numerical method to detect various of SPT phases, and also decoherence quantum channels for quantum computing. Today, he will talk about robust teleportation of a surface code. So please, Guo-Yi, it's your turn.
Thank you, Yizhi, for your kind invitation and your introduction. Hello, everyone. It's my pleasure to share with you our latest work today. It's about a teleportation of a topological surface code state. So let's remind ourselves a little bit basic notion about the quantum teleportation. So it was proposed in 1990s, and the basic idea is the following. Imagine that Alice have a quantum state, which can be represented as a cat state, our favorite Schrödinger's cat. And then in order to teleport the quantum state from Alice's hand to Bob's hand, so we need some entanglement resource. And this can be visualized as preparing an entangled pair. And then we share this pair between Alice and Bob that gives you a spooky wire. And then in order to do the teleportation, what Alice has to do is to just invert this process. You close the loop by performing a Bell measurement. Roughly speaking, you create a Bell pair and then you annihilate a Bell pair, and that closes the loop, and that gives you a complete quantum wire that can just transport the Alice cat state into Bob's hand. But of course, we cannot beat the speed of light. So we still need a classical communication channel to pass Alice's measurement outcome to Bob's hand in order to fulfill this process. Okay, so this is the theoretical notion dating back to 1990s. So what now? So what has been going on? So in experiment, people have been working extensively to progress this idea from theory to experiment, from very short distance to extremely long distance, up to 1,000 kilometers between the satellite and the Earth's surface. But on the other hand, we know that there's still a gap between the science and the fiction, the teleportation that we saw in the Star Trek. So what sits between them? So it's actually a gap between the field body physics to the many-body physics. So in the quantum communication field, people are also striving to teleport from one photon to multiple degrees of freedom, but it is still not yet the many-body case that we think about. So, but now we know that there's something lying in between. What is it? It is the NISQ. So now we have various quantum platforms which give us dozens to hundreds of qubits, which is noisy, but it's already far beyond a field body barrier. So one natural question is, can we teleport a reasonable and physical, robust many-qubit state out of dozens to hundreds of qubits? So this is the question. And in the following, I'm going to share our work towards this idea. And this is in collaboration with Finn, our student in Cologne, and Simon Traps, and Bohan from Weizmann Institute. And I also would like to acknowledge some inspiring discussions with Jason and Lisa. Okay, So let's start with a more detailed motivation. So now the basic idea is to teleport a many-body state from Alice's hand to Bob's hand. And then we live in a world which is imperfect. So generally we have some error that can hit the quantum wire. So the question is, can we teleport such a quantum matter under the coherent error? And we know that generally it's hopeless because there is the notion called orthogonality catastrophe. So if you have some finite error, and then you will realize that the many-body wave function that has been teleported to Bob's hand, its fidelity with Alice's original wave function must decay exponentially with the number of the particles. So it seems hopeless to teleport an exact wave function when there is error. But do we care about that when we talk about teleporting a quantum matter? Actually, not always, because we know when we talk about a quantum matter or a quantum many-body phase of matter, we care more about the order parameter rather than a specific wave function. And for this order parameter, more often we will see that the order parameter will approaches exponentially to a constant value, even though there is some finite perturbation. So for example, we can consider teleporting a robust and also useful many-body state. And what is it? So the first thing that came to our mind is this topological order, which does not require symmetry. So here, allow me to briefly review what do we mean by the C2 topological order. We can also roughly call that a quantum loop gas. So just think about a vacuum, and then inside the vacuum, you can just create some electric flux loops. Just think about Faraday. And then you can create more and more electric flux loops, but they don't have the ending point, so they just form some loop. And so these are some very classic state that you can have. And then you can think about superpose them together to form a quantum loop condensate. And this is exactly the topological order state that we talk about today. But then what if there is some loop which breaks open, and then you have an ending point which gives you an electric charge? This is possible. For example, you can pump in a open electric flux string which ends at this electric charge here and here and here. But then you can just add energy penalty to penalize this electric charge, or you perform some error correction to remove them and don't allow such a state to happen, to occur. And then you realize that you still allow another possible state, which is you pump an electric flux loop across the system without leaving any endpoint in the bulk. So this is also physically allowed because there's no electric charge created in the bulk. So in the end, you have these two states which are topologically degenerate because you cannot tell the difference locally. If you just look into the microscopic detail, you can't tell this state from the other state. And what that means is that it allows you to embed a single logical qubit into this many-body wave function. And so other than this picture, so how can we realize that? Yes, there is a rigorous, exactly solvable model that can realize this physics, which is called the torical model, also called the surface code model, depending on your boundary condition. In the following, I will just call them the surface code. So you can put your qubit on the bond center of such a lattice, and then you apply this vertex interaction and a plaquette interaction. It's 4-body Pauli C and then 4-body Pauli X. And if you diagonalize this Hamiltonian, then you can find the twofold degenerate ground state on this lattice. And on top of that, you can have some excited state by just apply a string of C, which creates an electric charge, or you apply a string of X, which creates a magnetic flux M particle. And then if we walk away from a Hamiltonian, just think about a quantum circuit in a quantum computer, then you don't have this Hamiltonian, but rather you implement the Hamiltonian effectively by performing a four-body measurement. That means you perform a four-body vertex measurement here to detect the electric charge and then remove them. And then you perform a four-body measurement at the plaquette center to detect the magnetic flux M particle, and then you remove them. And then in the end, you again get the same state as the ground state of the Hamiltonian. And this is the quantum state that you can have. So the next question is, are they robust? Right. So let's say you have this ideal Hamiltonian, and now you have some magnetic field. When you think about the Hamiltonian realized in the solid, and then you have magnetic field. Do you still have the same phase or not? Or in the circuit, you can think about some noise that hit the circuit, and then you ask whether you still have the same phase or not. So people have found that yes, it is robust. There is a finite threshold. So starting from this quantum loop gas ground state, you need a finite magnetic field to break it into a trivial paramagnet. This is for the Hamiltonian transition, which is a transition for the pure ground state. On the other hand, in the quantum circuit, when you add this Pauling noise, people also find that you need finite noise error rate in order to dephase this quantum loop gas into a classical loop gas. And that corresponds to a mixed state phase transition. So now we know that this is a robust threshold method that can have finite threshold. So let's come back to the question, can we teleport them, right? So now imagine that you have prepared this state and now you want to teleport with some error, and then you ask, what do we get after that? And what happens if your device group up at the critical point? And we want to advocate that this protocol that we will talk about is quite feasible and also timely in the current reconfigurable Rydberg atom systems, and also some trapped ion systems, and possibly the superconducting quantum processors. Okay, any questions so far? If not, I will just proceed. So let us look into our protocol. So now let's prepare a surface code, which is schematically shown here in this lattice. And it has the smooth boundary, which is called the M condensed boundary, and the rough boundary, which is called the E condensed boundary. And to represent as a circuit, we just use an encoder. The encoder just bring a trivial product state into the surface code state. And then we need to prepare the entanglement resource, which is a bunch of bell pairs. So we create a bunch of bell pairs and then share them. Half of them get into Alice's hand as A prime, and half of them are thrown to Bob's hand. And that can be visualized in the circuit by this wire. What this wire means is that A prime and B is exactly the same state, because they're just connected by a wire with nothing in between. And then, so we have finished the preparation of that bell pairs, and then what we need to do, in this surface code is to encode the logical information into the surface code at Alice's hand. So this logical information, we will call that reference denoted by R, and that will be useful in later when we come to chart out the phase diagram. So we pump this logical information into the surface code, embed that into the large Hilbert space of the Alice of the surface code, and then we perform the bell measurement. To perform the bell measurement, we basically couple the qubit between A and A prime by an RXX maximally entangling gate, and then we just measure each of them in the C basis projectively, and then it's done. So if you do this and share the measurement outcome with Bob, and then you can visualize an information flow from the logical information from this reference all the way to Bob's hand. So far, so good. This is the perfect teleportation protocol. But what happens if you have some coherent error here? For example, if A and A prime is not maximally entangled, but just weakly entangled, that means here you do an imperfect Bell measurement. And then we will ask where is the threshold and when does this protocol fail? And in fact, we can also insert another single qubit rotation here to change the basis of this imperfect Bell measurement. And then, as we will show later, this sometimes can do you good because it can enhance the threshold by tuning the theta and phi angle here. So that counteract the coherent error induced by parameter T. So this is the protocol. Is there any questions so far?
Yeah, I probably have a naive question. So does this protocol only work for abelian state, or can it also work for some non-abelian state?
Oh yeah, in this case, it can work for arbitrary quantum state because if you prepare the perfect Bell pair and then you will perform the perfect Bell measurement and then you share all the information faithfully from Alice to Bob's hand, then you can do that for any state. Yeah, this is just generalizing the teleportation idea from one body into many body.
Right, thank you.
Yeah, thank you. Okay, then I will continue. So we are going to diagnose the phase diagram. So now we have, as I say, we have a coherent error T, which governs the imperfection of the Bell measurement. And then we introduce a angle rotation that can possibly counteract the coherent error. So we have this phase diagram where parameter T is compactified from 0 to pi/4. That is denoted by this radial direction. And then we have this angle. So how do we diagnose the phase diagram? The idea is the following. So we can cross-grain our circuit into this information flow. We have this reference, which is a reference. You can also view that as a judge, right? So that pump the logical information into the system, and then if the teleportation succeed, that we get to Bob's hand. But now along this quantum wire, you have some coherent error here, and Alice also performed a measurement that can read out some information. So this logical information may possibly leak to the measurement outcome of Alice, or it will get just teleported to Bob's hand. So there can only be two consequences because you can never clone the quantum information here. This logical qubit cannot be cloned. So it's either at Alice's hand or at Bob's hand. So how do we quantify this information flow? So there's a standard diagnostic, which is called the coherent information. So you basically ask this conditional entropy between the reference and Alice. This Alice is the measurement outcome of Alice. You look into this conditional entropy to see whether the information of R ends into the measurement outcome of Alice. Yeah. And so this tells you whether Alice is still the key. And then you can derive that this quantity is equal to the following quantity. And what this quantity tells you is that whether Bob can decode the quantum key with the classical information shared by Alice. Because here you can see this is the negative conditional entropy between AB and R. So that just tells you whether AB together can learn about the reference qubit. Okay, and then one can further rigorously derive that it is equivalent to this quantity, which is a ensemble. This ensemble, by this ensemble, we refer to the measurement outcome ensemble, because S is the measurement outcome of Alice. And then if you repeat this protocol many times, then you have many measurement outcomes. And then if you do an ensemble average over the logical entropy of Bob's wave function. Remember, Bob get an imperfect statistical wave function, and you can look into its logical entanglement entropy that tell you the size of the code space, and then you average over the measurement outcome that also give you the same quantity. So this is the physical meaning of this quantity that we use to diagnose the phase diagram. And then this is to flash you the final results. So this is what we find. So within this blue shaded region, the teleportation protocol succeed. So that means if the coherent error is below this threshold, then Bob can decode the surface code wave function. In the following, I'm going to show you how we do this. Good. So first, we need to understand what's happening to each qubit.
Can I ask a question?
Sure.
In the previous graph, what exactly are the Z and the two axes over there?
Oh, thank you for asking. Yeah. So this is a compactified phase diagram. So T characterizes the coherent error, which goes from 0 to pi over 4. Yeah. And then there is an angle theta here. Theta, you can roughly view that as the angle of the Bell measurement. Because you know, when you do Bell measurement, there are many different bases that you can choose. So you can count the angle, and this is the angle that we count. Yeah. So that just take a one-dimensional phase diagram from 0 to pi over 4, and then rotate that, to get this quadrant. And then beyond this quadrant, it's equivalent. So you can just fold it back. Yeah. Yeah.
Okay.
Yeah.
So I mean, is it like safe to say that you're looking at something in radial coordinates, like not in planar coordinates? Like you have a coherent error, which is like the radius, and then you have the angle.
Exactly. Yeah.
Okay.
The radius is the coherent error. And that at the worst scenario is pi over 4. Because if you go beyond pi over 4, you come back. Yeah, because it's a rotation. Yeah. Okay, thank you for asking. Yeah. Don't hesitate to ask any clarification question. Okay. So first, we need to understand what's happening to each qubit at Bob's hand, right? So Alice have this perfect surface code, and then we teleport that to Bob's hand. What happens? So if we look into each qubit, so let's say this qubit at Alice's hand, and this qubit at Bob's hand. So their difference is the following. So this is one building block of the quantum circuit. Yeah. So this is Alice qubit. This single qubit state enter into this circuit, and then what comes out is the Bob's qubit. Yeah. So if you cross-grain this in this circuit building block, then it is equivalent to this operator. Yeah. And this is a non-unitary operator because there's an exponential of beta SC. There's no imaginary time unit I here. So this is real. So this is a non-unitary operator rather than a rotation. So this is the effective operator acting on Bob. So you can view the process as the following. Due to the imperfection of the Bell measurement, Bob get the wave function, which is exactly the same as Alice, but then this wave function suffers from this cross operator. Yeah, then there is this error operator acting on Bob's qubit. And that operator, if you look carefully, then it mimics a magnetic field because for beta is real. So for very large beta, they will just try to polarize the qubit in the Z direction, right? And that depends on the measurement outcome S. whether it's S is plus or minus. Yeah, that just try to polarize Bob's qubit in C plus or C minus direction. So we can just visualize that as a magnetic field turning on Bob's wave function. And that magnetic field can vary from side to side. Yeah, that depends on the measurement outcome. Okay, and then we want to make a remark that this circuit diagram, in the end, if we cross grain it, it's just one matrix, right? Because there's only one wire coming in and one wire coming out. That is effectively a single body non-unitary matrix, and that matrix is equivalent to this matrix. Yeah, so if you can alternatively, if you forget anything about teleportation, you just have a surface code and you perform a weak measurement, then you have the following circuit diagram, and this gives you exactly the same Krauss operator. Yeah, so the teleportation with imperfection is equivalent to a weak measurement. Okay. Then so what? So this is happening on each qubit at Bob's hand, but then we are most interested in the perturbation to the logical qubit, because that is what we care about most. So in order to understand how this error acts on the logical qubit, we can simply project this error operator into the logical space. So here, the psi mu and psi nu corresponds to the logical state. Remember, we have two macroscopic quantum wave function, psi 0 and psi 1, which denotes the two degenerate state. And now we project this error into that two-dimensional subspace. And then you can realize that you can represent it as a 2x2 matrix, and that can be viewed as one logical qubit suffering from some magnetic field. They try to polarize it in the Z direction or the X direction. That depends on your polarization field. Yeah. So if you have a effective magnetic field along the Z direction, you will dephase this Bloch sphere into a classical, from a quantum bit into a classical bit. Okay, and then so what is the physical meaning of this magnetic field? How come such a magnetic field? We can just write down this magnetic field, and then we can understand that actually they are contributed by the anyons quantities in this case. So if you look into the anyon mechanism, then you can realize that this term basically captures the confinement contribution. So the confinement contribution is tells you whether the E particle is allowed or not. So this is the psi plus, this is the one wave function, and this is psi minus, which is another wave function. They are related by just pumping an electric flux tube across the system. So if electric charge is confined, then you are not allowed to pump this electric flux loop, and then you don't have psi minus. So and then that will contribute to this component being 1. Yeah, and then you will have a finite magnetic field in for this component. And on the other hand, E particle could be condensed due to the error. And if E particle is condensed, that means out of the vacuum, your E particle can just randomly pop up. And that means you can easily pump an electric flux loop across the system without costing energy. And what that tells you is that this psi plus is no longer distinguishable from psi minus. And what that tells you is that this P plus minus, which is the overlap between the two states, becomes finite. So to summarize, the two components of this effective magnetic field come from the condensation contribution and the confinement contribution. Yeah, so that is an anyon mechanism interpretation for the magnetic field that act on the logical space. Okay. Now, with all this thing, we can move on to understand the phase transition. So let us start from a simple example where the angle theta is just a shutdown to be 0. Just fix an angle along the C direction. And then, as I said, after Alice performed the Bell measurement, Alice qubits is collapsed into classical state, which is denoted by S. And correspondingly, Bob get a perfect torical, perfect surface code psi with a cross operator in this format. Yeah, so this is a cross operator that mimic a magnetic field acting on Bob's wave function. And then let's ask, what is the phase transition? So if we tune the parameter T from 0 to pi/4, then this effective magnetic field beta will go from 0 to infinite. And correspondingly, these cross operators go from identity operator to a projective operator, because in an infinite strong magnetic field, you just polarize the qubit in the C direction. And so, you know, in this limit, you have the perfect surface code. And in this limit, you just polarize everything into a trivial paramagnet. And then you know there must be a transition in between. And in order to understand the transition, we can just take this wave function and then map that to a random Born Ising model. And this random Born comes from the random measurement outcome out of the Alice measurement outcome. So this is a random Born Ising model. And if we just briefly review the classical phase diagram of the random Born Ising model, then you will see this. Usually, when people talk about a classical random Born Ising model, they have a two-dimensional phase diagram. They can tune the temperature and they can tune the disorder because there's a lot of randomness here. And then they have the ferromagnetic phase and the paramagnetic phase. But now, in our case, we have only one parameter, right? And actually that tunes not only the disorder, but also the temperature. Because if you look into the disorder here, the disorder is given by the Born's rule, which is equivalent to the thermal partition function. So what that tells you is that Born's rule guarantees that the effective disorder conspire with the effective temperature. And then you are bound to track along the Nishimori line in this classical phase diagram. So in the end, it's a delusion that you have both disorder and temperature, but rather you have only one source of fluctuation that keep you along this line. And then you can chart out a threshold, which is at 0.143 pi here, by just adapting this critical point, which has been known before, into this case. And then you will learn about the phase transition in this case. And now let us move on to rotate the angle of the measurement, right, away from the C axis all the way down to the X axis. And then we have the following phase diagram. So we first, we can perform numerical calculation to check that along the C and the X axis. And then we can calculate the coherent information, which goes from 1 bit of log2 down to 0. And we can do perfect finite size collapse to find out the critical exponent and the critical location, which is consistent with the Nishimori critical point at 0.143 pi. Okay, so far so good. And then what happens along this diagonal direction? Let me comment that along the diagonal direction, the system has an enhanced symmetry because the surface code has two types of particle, the E particle and the M particle, and they are dual to each other. And so the C direction fluctuates the E particle, and the X direction fluctuates the M particle. And so if you go along the diagonal direction, which is symmetric between a swap of C and X, formally you can write that as a Hadamard transformation. And then this protocol is always invariant under the Hadamard transformation. So even the error is invariant under the Hadamard transformation, which means the protocol is electric magnetic self-dual. So E and M particles are always on equal footing. And then you will realize that from numerics, you immediately see that the coherent information always approaches exponentially fast to 1 bit of log 2. So it never decays to 0 unless you fine-tune your protocol to enhance the error to its maximum. So unless you are at pi/4 coherent error, otherwise, you always get 1 bit of coherent information, which means you always have the topological order phase, which point to a maximally stable topological order when you respect the electromagnetic self-duality. Okay, so more generally, between these two limits, along the C or X direction or along the electromagnetic self-dual direction, we perform numerical calculation to find out these dots, and then this gives us the following phase diagram. So what we learn is that the threshold of the coherent error depends on the angle of the measurement. And the physical understanding is that when you tilt the angle of the measurement, you are allowing both E particle and M particle to fluctuate together. And they compete with each other. Why do they compete with each other? It is because if you take an M particle and wind it around the E particle, you get a pi phase. So E particle is just like a vortex for the M particle. And so you cannot condense them simultaneously because there is the destructive interference effect. And so the maximal frustration of such anyon condensation is along the self-dual line, because then E and M are fully on equal footing. And what we find is that you have an infinite threshold. We call this infinite threshold because it's at T equals pi/4, which is translated to infinite beta, which means 0 temperature. So you can view this axis as effectively lowering your temperature in the classical model. So it's from high temperature to low temperature. So so the anyon never condenses until at the limit of the 0 temperature. So on the other hand, what that also tells us is that, well, your teleportation will always succeed for infinitesimally recoupling between Alice's original wave function and half of the Bell pair. So that is the maximal direction. So you would like to, in practical experiment, then you would like to can the angle away from 0 to pi/4, because that enhances your threshold, and that gives you a higher chance to successfully teleport the surface code. So this is the phase diagram. Any question?
Yeah, I have a question. So I wonder for other stabilizer code, which also have such kind of anyonic symmetries or self-dual symmetry between E and M, do we always expect such kind of line where you have a stable, coherent information?
Very good question. We don't know. But very generally, we don't know. Now we are still working on whether there is a higher principle behind that. Yeah. So what we can anticipate is that when your error respect the self-duality, then you will have a higher threshold. But whether the threshold is always infinite, we don't know. But for torical, in many cases, in many different kind of noise of torical, as long as they respect the self-duality, then they can exhibit the infinite threshold. Yeah.
I see.
Yeah.
And also previously in Edud, Altman, or Ashvin, or Tsenker's work, when they consider only X and Z arrow, they can demonstrate that in the Cho-doubled space, it's something like anyon condensate in the time domain, or from space-time rotation, it's something like anyon condensate at the boundary. I wonder along the X plus Z line, can we understand them in terms of some type of anyon condensate at the boundary?
In our case, it's also anyon condensation. The
Mhm.
difference is that in the mixed state transition,
Mhm.
the one that you refer to, what they were working on, that is anyon condensation in the double Hilbert space.
Yeah.
The wave function cat and the wave function bra in the double Hilbert space. But here, as I said, so for each measurement outcome of Alice, Bob get a pure wave function, which
I see.
suffers from some effective random magnetic field. So it is
I
anyon
see.
condensation in the single Hilbert space.
I see.
Yeah.
I see.
Yeah.
All right. Thanks.
But at the later part of the talk, I will come back to comment on more along the direction. Yeah.
All right. Thanks.
Yeah. Yes. And okay, good. So let's continue. So how do we calculate all this stuff? So in the following, I will just briefly mention the techniques, which also give you some insight how do we come to this conclusion. So first, we can write the wave function using a PAPS. This is a tensor network representation of the wave function. And on top of this wave function, one can apply a string operator of C to create the E particle. And one can also apply a string of X to create the M particle. And the advantage of the tensor network is that there is some tensor network rule that you can play with to reduce the string. So you can pull the string through and then reduce that to just a 2-point correlation, sigma in the classical world. By classical world, we mean the virtual index of the tensor network. And then the string of X can also be pushed through from the physical lag into the virtual lag. And then that places the meaning as a domain wall in the classical model. Yeah. So, and then you can chart out this dictionary between the anyon of the toric, which is the E and M particle, and they correspond to the classical Ising spin and the classical disorder operator, which creates a domain wall in the classical model. So the very important property is that this relation still holds even if you have some local non-unitary deformation acting on the physical lag, because now you have a lot of this error gate acting on the physical lag, but they do not affect what's happening in the virtual lag. Yeah, so this mapping still work. So this is some key trick, and then we can just take this wave function and then take its cat and its bra and then sandwich them together and then compress the network into a 1+1D random circuit. And it's random because here each error gate has some randomness. So that corresponds to a 1+1D random circuit, and that 1+1D random circuit can be interpreted as a 2D classical 8-vertex model. Yeah, you can forget all this detail. On a very high level, it's just mapping from a 2+0 dimensional wave function to 1+1D circuit to 2D classical model. And a basic physical understanding is that
can I just ask I mean, it's how do you get the one time axis when going from left to right? Like, how does one space axis become a time-like axis? Because you are right now as 2+0, right? And then you go to 1+1. Does that refer to space and time? What do you refer? What does 1+1 mean?
Oh, 1+1 just means 2D. So here, you can view this as a network, just a classical model. And then you can just take one spatial direction as a fictitious time. And then you can view this as a one-dimensional quantum state undergoing a circuit evolution, which is non-unitary. Yeah.
Okay, thanks a lot. So it allows you to compress this into a one-dimensional.
Yeah. And that is how, and that is in the end, that is how we do the calculation. So numerically, we just start from the boundary MPS. We view this as a one-dimensional quantum state, which is written as a matrix product state. And then we evolve it in the vertical direction by just applying this non-unitary gate onto that, and then keep evolving. Yeah, this is just the standard transfer matrix method as common
Right.
applied in statistical mechanics. Yeah.
Thanks for that clarification.
Yeah. And then, we can concisely write down the effective classical model in the following. So it's 2 layers of Ising spin. And why there are 2 layers? It is because we take the wave function cat and the wave function bra. So the wave function cat of a surface code is due to a classical Ising model, right? And then we have a wave function bra, which is also due to a classical Ising model. So that's why we have 2 layers of classical Ising spin. And now the error rate, the error gate will hit the wave function cat and bra simultaneously, right? And that will induce the interaction between the 2 layers. So in the end, we get this Ashkin-Teller model, which is 2 layers of Ising model coupled together. And this is the classical model. Good. So we can further show a dictionary of the physical observable from the physical quantum wave function, the anyon E and M, and this contribution to the coherent information, and map that to some spin-spin correlation in the classical world. And that spin-spin correlation is again represented as a spin-spin correlation in the effective 1D XXC chain. Yeah. Here we introduce the 1D XXC chain because this circuit, it's actually a XXC circuit, the anisotropic Heisenberg spin chain. Okay, so this is a very technical detail. Let us move on and just see what that brings us. To understand the StatMech better, we can take a analytical trick, the replica trick. So one can ask, if we try to calculate not the von Neumann coherent information, but the nth order Rayleigh coherent information, which is given by this formula. So you take the density matrix, and then you replicate that up to n copy, and then you trace it out. And then you will realize that you can trace out the disorder and then get a clean system which give this phase boundary. So now for this n equals 2 replica, we get a phase boundary along this red dots, this red line, rather than the blue line. So when you go to, that means when you go from the von Neumann coherent information into the second order Rayleigh coherent information, you shrink the topological phase from this threshold to this threshold. But the advantage of this is that we have some insights about what is the universality class of the transition here, because we can exactly map that to a Ising model, which also tell us the threshold, which is consistent with the numerical calculation. And then in this 2 replica limit, we can also perform a calculation along the electromagnetic self-dual line to see whether we also have the infinite threshold. It turns out yes. So this is the second order Rayleigh coherent information, which also show an infinite threshold up to t equals pi4. Yeah. And then from the monotonicity of the Rayleigh entropy, and then you know that this second Rayleigh threshold will lower bound the threshold of the von Neumann coherent information. So if this set 2 replica limit is already at infinite threshold, then it again corroborates that the von Neumann limit must be also at infinite threshold. Yes, and then we can understand better what's happening at this infinite threshold limit. What is the underlying theory of that? We can realize that in this 2 replica limit, we have effectively 4 layers of Ising spins, because we have 2 copies of the density matrix, and each density matrix have wave function cat and bra. So in total, you have 4 layers, and these 4 layers have permutation symmetry. So you can just reshuffle any layer and the model is invariant. And this S4 symmetry emerges at this asymptotic limit when your coherent error is maximal. And then at this point, this is the self-dual point. We perform numerical calculation for the boundary entanglement entropy to verify the effective central charge, which is almost 1. Yeah, and that is consistent with the analytical expectation that this critical point is governed by the 4-state Potts conformal field theory. So, and then what happens if we further going to a higher replica limit? For example, if we go to the infinite replica limit, and that is to take the P, which is the probability of the measurement outcome, to a power of infinite. You know, taking it to a power of infinite, we just distill out the most probable configuration, and that configuration is the clean configuration, and that also corresponds to a post-selection scenario. In that case, we learn about this phase boundary by exactly map that to the clean Ashkin-Teller model. So on the left-hand side, I show you a non-random Ashkin-Teller model phase diagram, which is exactly solved. And this is the phase boundary. So you have two Ising transition lines that merge at a 4-state Potts point, which is permutation symmetric. And then that enters into a gapless line, which is governed by a central charge equals 1 conformal field theory. It's described by the free boson field CFT. And that tell you the phase boundary of the infinite replica in our quantum protocol. So this is it is shown here. And then you can see that when you raise the replica limit from 1 to 2 to infinite, you monotonically decrease your threshold from this to there. So this is what we call a cascade of the transition. In the end, before we make a high level comment, let me just show you this result along the diagonal line. So if we take this post-selection case and again track the self-dual direction, and then we calculate the coherent formation, which surprisingly also show a very good finite size collapse here. It's a very good crossing point, which is consistent with the 4-state Potts critical point that we know analytically at pi-8. One significant feature is that we know that usually if you ask a condensed matter physicist to calculate the costless storage transition, it's rare that you can see such a perfect crossing point. But for this coherent information quantity, it shows very perfect crossing point here, just like the Binder cumulant. So this is a side remark. In the end, if we look into this phase diagram at different replica limit, what does this cascade of transition tell us? It just tells us what is the ensemble of the state that Bob can have. Because we perform a teleportation protocol, Alice have to perform measurement, and the measurement outcome is random. So that means Bob get a random post-measurement quantum state, right? It's random. So if you repeat this protocol many, many times, in the end, what Bob has is an ensemble of pure state. And if you try to learn about the distribution of this ensemble of state, you can just do so by tuning this parameter n, and that will tell you a different fraction of the ensemble of the state. Yeah, so this is what this tells us. Okay, any questions so far? Good. If not, I will continue to talk about decoding, because so far it's just a theoretical understanding, and we do numerical calculation to show the phase diagram, and then how do we decode that? Do we need to create such a lab to do that? Actually, the idea is very simple. So in order to decode this problem in a quantum experiment, it's basically to ask who has the key, because the quantum key cannot be cloned, right? So it either ends at Alice's hand or Bob's hand. So to do so, we can first ask whether Alice has the key. So we can evaluate the conditional entropy that can tell us whether Alice steals the key. And this idea is in the same spirit as the scalable decoder for entanglement phase transition proposed in this reference. And more interestingly, we would like to ask, how can we decode the information from Bob's hand? Because in the end, the surface code is teleported to Bob, and Bob may want to use this surface code to do something in future, right? And for example, if Bob want to use it for distributed quantum computation, yeah, so can we do some error correction there? So this is the idea. So the idea is the following. So first, we consider a very naive protocol, which we call the passive teleportation. So imagine that Alice have this bunch of qubits, and they have performed the Bell measurement to collapse all of them. And then Bob gets a state out of this spooky wire, right? And in order to complete the teleportation cycle, Alice must send the measurement outcome via a classical communication channel to Bob. Remember, we cannot beat the speed of light. Yeah, so we have to send the outcome from Alice to Bob. And this is a naive way to do so. We just ask Alice to send each outcome to Bob, and then we apply a simple single qubit local feedback for each qubit of Bob. So that means if the measurement outcome is negative, say A2 is negative, and then B2 just perform a flip. Yeah, very simple. You don't need a classical computer to do anything here. It's very local and conditional. And then you realize that if you have some coherent error at Alice's hand, yeah, the parameter T, as we talked about earlier, and then that will it leads to a effective noise for Bob's qubit. Yeah, so in the end, if you repeat this experiment many times, what Bob gets is a noisy state under this channel. You can understand this by the following. It's like the error at Alice's hand can be propagate into the classical communication channel, and that can be further propagate to Bob's qubit. Yeah, so in the end, it's equivalent to applying the noise on the state. But because we are teleporting this topological surface code, which is a quantum error correction code, so you know that is a finite threshold. Yeah, in this case, you can see that the effective noise probability is related to the coherent error T according to this formula. Yeah, this is akin to the fault-tolerant of the coherent error. And then by adapting the well-known noise threshold for the surface code, you get a threshold at 0.107 pi. Yeah, this is the mixed state transition. Yeah, and then if you remember what we talked earlier, then there may be an alarm because, well, the threshold that I showed earlier is not here. Yeah, it's not at 107, but it's higher. And I also said that our transition was a pure state transition, but here it is a mixed state transition, right? What's wrong? What goes wrong? What goes wrong is the following. So this we call that the passive teleportation, and then what is the opposite? The opposite is an active teleportation, and that means rather than just trivially send Alice's measurement outcome to Bob one by one in a pairwise manner, we can insert a classical computer in the middle to process all the information. So that means there's not only classical communication between Alice qubit and Bob qubit, but also there is a classical communication between different qubits. Yeah, this is a many-qubit decoded feedback. And then with this, we can unveil the threshold up to 0.143 pi. Yeah. But what's funny is that both transitions corresponds to the random Ising Nishimori criticality. And to understand that, you can see that the problem, both the active and the passive protocol are mapped to random Ising model, but the temperature is different. So for the passive protocol, the parameter T going from small to large corresponds to the random Ising model from low temperature to high temperature. Because here T characterizes the noise. Yeah, so it is less noise, which is cooler, and here it is more noise, which is hotter. But for the active protocol, it's the opposite. Because for the active protocol, when T is very small, that means you do very, very weak measurement. And then your measurement outcome has maximal uncertainty. But when T is very large, then it's projective measurement. Yeah, so there is less uncertainty. So it's the random Ising model from hot to cool regime. So that's why this threshold is so symmetric. Yeah, it's not an accident that these two thresholds, if you add them together, it's exactly pi force. Yeah, they are symmetric because they map to a random Ising model with the opposite temperature tendency. Okay, so this is only for the limiting case of theta equals 0. But if you just perform this active teleportation with this decoder in the middle, then you can decode this phase diagram, yeah, for generic theta. Good. So let's skip something, and then in the end, so what happens is between them, right? I show you the passive teleportation and active teleportation. Can we tune between them? Yes. As I said, the difference just lies in whether you have the classical communication between different qubits. Yeah, not just between Alice and Bob, but also between different qubits. And then that can be tuned by turning on this noise in your classical computer, and that will bridge the gap between the active and the passive protocol. So I want to just make a brief comment that here in the generic phase diagram, we will have 3 phases. So we will have this surface cold phase, which is a quantum loop gas condensate. And then for the active protocol, when your error is very high, you undergo an anyon condensation in the single Hilbert space to drive it to a paramagnet. Yeah. But in the passive protocol, you effectively turn on the noise. We just dephase. Yeah, we just dephase the quantum loop gas into the classical loop gas. Yeah. So here, this is the anyon condensation, but not in the single Hilbert space, but in the double Hilbert space. Yeah. So what we know rigorously is this boundary line and these several points. Yeah. But the generic transition between them, we're still working on that. And one more comment. So this phase boundary is due to a Nishimori's cat realized in an IBM experiment in one of our collaboration work. Good. So now let me briefly summarize. So we have shown you that we can teleport this many-body topological order state together with its logical qubit. And in practice, when you perform this teleportation, you would like to cant your Bell measurement angle to respect the self-duality of the surface code, because that can optimize your threshold up to infinite. And secondly, that also allows us to realize an anyon condensation phase transition to learn about the topological order in this quantum experiment. And we can realize not only the anyon condensation in the single Hilbert space as a pure state transition, but also the anyon condensation in the double Hilbert space, which is a mixed state transition. And thirdly, our model along the self-dual line also tells you that we have a generalized model away from the random Ising model into a self-dual 4-state pod, which is still random bond disorder and has the Nishimori type disorder, but it is self-dual. And in the end, we want to advocate that this protocol is quite experimentally feasible in various current NISQ platforms. There's some outlook here. Thank you for listening.
Thanks, Guo-Yi. Any question? Yeah, Deepak.
No, I was just applauding. I think that's the applaud
Thank you.
emoji.
Yeah.
Yes.
Yeah, actually, I have a question. So if I'm not teleporting any long-range topological order state, just want to teleport some type of cat state in 1D and 2D, is it
Yeah.
stable?
Yeah.
Probably not stable like that.
Yeah, that depends
At
on
least
the
for lower
noise
dimension.
type. Yeah, that's stable against the noise type, which is which respect the symmetry, but it's not stable against the noise that violate the symmetry. Yeah, so cat state is still fragile. Yeah.
I see. So is it true that for robust teleportation, we probably need some topological order or higher form symmetry, such that whenever you have error, higher form symmetries or topological order would be more stable against that.
Yeah, yeah. Because you know, in the end, we just relate this teleportation transition to effectively to a weak measurement transition. So the question is equivalent to ask what kind of phasal matter is stable against weak measurement, right? And then you know that if you have a cat state, of course, it's unstable against some type of weak measurement that would collapse it, right? But yeah, along some other direction, it can still be stable. Yeah.
Okay, I see.
Yeah.
Thanks. So any other question?
Yes, I have one. Could you go back to the slide where you map into the Ashkin-Teller model, please?
Okay.
Probably you have said that, but at some point I missed. I have to
yeah, no worry. Yeah, please
step out and come back. Is disorder correlated in one direction, or it's totally random in space in both?
In both directions, it's all correlated. Yeah. So
so this Sij is actually, let's say, just Si or something like that. And the time direction is correlated. That's how you can map from.
Yes. So here by Sij, so Ij just denote the site. Yeah, site I and site J. So Sij is the bond disorder on the bond connecting site I and site J, but the disorder is highly correlated. Yeah. So it's not independent uncorrelated disorder. So what is the disorder probability? Let me show this slide again.
That's fine. Let me just ask you more precisely. For instance, when you said that Si and J, as you just showed before on the previous slide,
okay,
the next line on top of the one that you showed is the same bond disorder? Is the same bond?
No.
So yeah, that's the one. The one on top is the same one?
No.
No, top. The next line, not the first column.
Next slide.
The next row, you have a many rows.
At this row.
Yeah, is the same as Ij?
No, it's not. They always changes. So you can view this as a 1+1D dynamical problem, and the disorder fluctuate in space and in time.
Okay. So then how do you map that back to 1D quantum model?
Yeah, it is mapped to a 1D quantum model with space-time disorder. Because you can view this as a circuit, right? And then each slice can be viewed as a one-step evolution. But this evolution is disordered. Yeah, so you can imagine that from the bottom line.
It's like a new disorder. Okay, it's not quench disorder.
It's also not a nude. Well, it fluctuates in space and time.
It's quenched in the classical version, but in the quantum version, it has to be a...
Exactly. Yeah, it's not static.
Okay, thank you.
Yeah, thank you for your question.
Any other questions? Yeah. Okay, thank you. So this is Weltzman, probably.
Exactly.
Yeah.
Yeah.
All right. So if no question, let's then Guo-Yi again.
Thank you, Yi Zhu.
Thank you.